In this video, we will solve a question on constrained optimization using Lagrangian method. The question is given the utility function is u is equal to x plus 2 times y plus 1, where x and y are the two goods. Price of good x is 4 and price of good y is 6. Income is 130. We have to write the Lagrangian function first. Then we need to find out the optimal values of good x and y and the Lagrangian multiplier, and we need to interpret it. Okay, so let's write. We are being given the utility function u is equal to x plus 2 times y plus 1. Okay, so we can rewrite it in this fashion: xy multiplying this x to each of the terms here. So then we have plus x plus 2y plus 2. Okay, this is our utility function, and we have the budget constraint, that is price of x times units of good x plus price of good y times units of good y should be equal to the total income. Okay, so price of good x is 4, so we can write 4 times x plus price of good y is 6 times y is equal to budget of the consumer is 130. Our question becomes, then we want to maximize this utility function u is equal to xy plus x plus 2y plus 2. Okay, subject to the budget constraint, that is 4x plus 6y is equal to 130. Okay, so this is our question. So what first we need to find out the Lagrangian function. Okay, so Lagrangian function can be found by we add this utility function, and first we manipulate this budget function in such a way. If I transpose all the terms to RHS, so it will become 130 minus 4x minus 6y is equal to 0. Okay, so first we set this budget constraint is equal to 0, then we multiply it by lambda. Okay, so simple thing is to find out the Lagrange's function. First we need to manipulate this budget constraint. First we set it equal to 0 and multiply it by lambda. Then our Lagrange's function is the given utility function, what we call the objective function, plus this resulting budget constraint. So it will become 4x plus 6y plus this resulting budget constraint, that is 130 minus 4x minus 6y. Okay, this is our Lagrange's function. Now the second part tells us to find out the optimal values of good x and y. So we can find out the optimal values of good x and y simply by partially differentiating the given Lagrange's function with respect to x, y and lambda and set them equal to 0 simultaneously. That means L subscript x means partially differentiating this Lagrange's function with respect to x. The derivative of x is 1, so we are left with 4, and derivative of x here is 1, so we are left with minus 4 lambda. Okay, so I guess I have done some mistake here. Our Lagrange's function is, we have xy plus x. Okay, sorry. This is our utility function, that is xy plus x, xy plus x plus x, xy plus x plus 2y, 2y plus 2. Okay, let me rub this out. So our L is Lagrange's function is this the utility function, that is xy plus x plus 2y. So x plus, sorry, it is xy plus x plus 2y plus 2. Okay, plus this resulting constant. Okay, we partially differentiate it with respect to x. Derivative of x is 1, so we are left with y, plus derivative of x is 1, so we are left with 1, and derivative of x here is 1, so we are left with minus 4 lambda. So we have minus 4 lambda, and we set it equal to 0. Okay, and we rewrite it in this fashion: y plus 1 is equal to 4 lambda. Similarly, what we do, we take the partials with respect to y of the given rather of this Lagrange's function this time. So derivative of y is 1, we are left with x, plus derivative of y is here 1, so we are left with 2. Derivative of y is 1, so we are left with minus 6 lambda, and we set it equal to 0. That means x plus 2 is equal to 6 lambda. Then we partially differentiate this with respect to lambda, that means L of lambda is equal to, so since no lambda is involved in the first four terms, derivative of lambda is 1, so we are left with 130 minus 4x minus 6y. Okay, and we set it equal to 0. Okay, so we have three equations. This is for equation first, equation second, and equation third. What will we do? We divide equation 1 by equation second, equation 1 by equation second. So we have, which implies y plus 1 divided by x plus 2 is equal to 4 lambda 4 lambda divided by 6 lambda. Lambda gets cancelled, so we have 2 2s are 4, 2 3s are 6, so we are left with, which implies y plus 1 divided by x plus 2 is equal to 2 upon 3. Let us solve this. So this becomes 3y plus 1 is equal to 2x plus 2. That gives us y will be equal to, rather 3y will be equal to 2x plus 2, sorry, it is here 2x plus 4. Okay, 2x plus 4, so we have 2x plus 4, and transposing this, it will get subtracted. That means 3y is equal to 2x plus 3. That means let's divide both sides by 3. That gives us y will be equal to 2 upon 3 x. Am I doing it correctly or not? So 4 minus 1 is 3. Let me see here. I guess I have done some mistake here somewhere. So we have 3y into 1 is 3, so it is here 3. Sorry, I am doing some basic mistakes here. So it is here 3, so this will become 2x plus 1. Okay, so plus here we have 1 upon 3. Now we plug this value of y is equal to this stuff into the budget constraint, or in the third term. Okay, so let's plug the value into this third equation. So we will get 130 minus 4x, then we have minus 6. The value of y is 2 upon 3 x plus 1 upon 3. Okay, and it is equal to 0. So we have 130 minus 4x. Here 3 1s are 3 2s are 6, so we are left with minus twice x. Again 3 1s are 3 2s are 6, we will be left with minus 2, and we set it equal to 0. When solving this, this is minus 4x and minus 2x is minus 6x. Again I am doing some basic mistakes here. So 3 1s are 3, 3 2s are 6, so 2 2s are 4, it is here 4. Okay, so minus 4 is minus, sorry, when I transpose it, it will become 8x is equal to 130 minus 2 is 128. Okay, dividing both sides by x, we will get the value of x equal to 128 divided by 8 will be equal to 8 ones are 8, 9 da ka 48. So we get the optimal value of optimal value of good x is 16. To find out the optimal value of good y, so simply plug x is equal to 16 in this equation. That gives us y will be equal to 2 upon 3 times 16 plus 1 upon 3. Solving this, it will give us the value of y equal to 11. Okay, so we got the optimal values of good x and y. Now the third part tells us to find out the Lagrangian multiplier. For that, let me rub something here. Okay, let me rub this out. To find out the Lagrangian multiplier, what will we do? We simply plug the optimal values of x and y either in equation first or equation second. Let us solve it for equation first. So y, in place of y, we write the optimal value, which is 11 plus 1 is equal to 4 lambda. So 4 lambda, 11 plus 1 is 12 is equal to 4 lambda. That gives us the Lagrangian multiplier equal to 12 upon 4, which gives us Lagrangian multiplier equal to 3. And to interpret it, it simply tells us how does the utility changes when there is change in the constant of the budget constraint. Okay, simple thing. How much utility will change if the constant of the constraint changes. So what is the constant of our constraint? It is income here. Okay, uh, so it simply tells us we got budget, rather this Lagrange multiplier is 3. It simply tells us how much utility will change if there is change in the constant of the constraint. So the constant of the constraint is here 30. So it simply tells us if income increases by 1 unit, okay, utility will increase by 3 units. Okay, let me repeat it here. Lagrange's multiplier simply tells us how does the objective function changes when there is change in the constant of the constraint. Objective function is utility function, okay, and constant of constraint is income. If income increases by 1 unit, our utility function will increase, rather our utility will increase by 3 units. I hope I make myself clear in this video. Thank you.